Hello friends, welcome to the Formula Engineering classroom. And in the last lecture we discussed about the buoyancy and the flotation concept. In this lecture we will see some numericals and also we will discuss the concept of stability of submerged and floating bodies. So let first problem I am taking here, so that I am saying, so some stone is given and its weight is given, and it's saying there is weight of this stone in air. Weight of this stone in air is 392.4 Newton. So this is the weight of the stone is given in the air. Similarly, for the same stone, the weight in water is also given. Okay, in water, the weight is given is 196.2 Newton. And in this case, we want to calculate the volume of this stone. Okay, so we want to calculate volume of this stone. Okay, so when the stone is in air, so if I'm saying the stone is in, that this is our stone here, this is in air, this weight is 392.4 Newton. But when the same stone is submerged in the water, then we are feeling less weight in this case, that we are feeling 196.2 Newton weight. So we, in this case, when this stone is submerged in the water, so in that case the weight is less, because in that case the buoyant force is acting on this stone, that is acting in upward direction. So some of the weight is nullified by that buoyant force. So that's why we are feeling less weight of this stone in the water. So we can say that, let's suppose if I'm saying this is our water here, okay, and this is our stone here. So the actual weight we are saying in air is 392.4 Newton, and in water we are feeling 196.2 Newton. So the buoyant force will be obviously the difference of this weight. Okay, we can say that there is weight we are feeling in water is 196.2 Newton. This is the weight of the stone in water, and there is some buoyant forces acting here, and we want to calculate this one. So we can say that this buoyant force FB will be simply the difference of weight of the stone in the air minus weight of the stone in the water. So we can say that this is 392.4 minus 196.2 Newton. So this difference will be actually equals to 196.2 Newton. This is 196.2 Newton. Okay, this is our buoyant force, and this is actually acting in upward direction. So our buoyant force that is acting on the stone is 196.2 Newton. This is the buoyant force. But we are interested to calculate the volume of this stone. Okay, so from our previous discussion we can say that a buoyant force is nothing, it's simply the weight of fluid displaced by the body. Okay, so we can say that this buoyant force FB is actually weight of fluid, that is water. So weight of water displaced by stone. Okay, so how can we calculate this weight? So we can calculate this weight by saying there is specific weight of water into volume displaced of water. Okay, so now we know this value FP. So I think this value is 196.2 Newton, and obviously we know what is the specific weight of water, that is I think 9810. So we can say that this is 196.2 and this is 9810, and this is the volume. Okay, so from here we can say that the volume displaced of fluid this one, volume displaced of fluid, that is water, is equals to, so by the calculation we can say that this value will be equals to 2 into 10 raised to power 4 centimeter cube. So this is the volume of water displaced by the stone. And you can see this one, that is, as the stone is completely submerged in water, so obviously this will displace as much as volume as the volume of the stone. Means the stone volume and the displaced water volume is same. Okay, so from here we can say that this is also equals to volume of this stone. Point is clear? Okay, now we are interested to calculate the weight of this, sorry, not weight, actually mass of this stone. So I think the weight of the stone in the air is given and we want to calculate the mass of the stone. So we can say mass of stone simply will be weight of stone in air divided by g here. Obviously we can say W is equals to simply mg. So from here we can say that, so mass of stone, so weight of stone in air is 392.4 divided by 9.81. Okay, so by the calculation of this one we can say that this is equals to 40 kg. Okay, so 40 kg is the mass of the stone. Now, so if we know the mass of the stone, we can also calculate the density of stone. So we can say that density of stone will be simply equals to what? So I think we can calculate density will be simply equals to mass per unit volume. So mass of stone divided by volume of this stone, and we know the volume of the stone, that is 2 into 10 raised to power 4 centimeter cube. So mass of the stone is 40 kg and volume, so we can say that this value is 0.02 meter cube. Okay, so from here we can say that the density of this stone is 2000 kg per meter cube. Okay, so the density of the stone is known, that is 2000 kg per meter cube. Now as we know the density of the stone, we can also calculate the specific gravity of the stone. So the specific gravity of the stone will be simply density of stone in air, obviously, divided by density of water. Okay, so density of stone is 2000, this is 2000, and density of water at 4.4 degrees centigrade and atmospheric pressure we can say that 1000. So by the calculation this one we can say that this is 2. So means the specific gravity of the stone is 2, means the stone is twice the dense of water. So obviously this will submerged and this will completely going to be sink down in this water because this is twice the dense of this water here. Okay, let's take one more problem here. Okay, in our next problem the body dimensions are given. The dimensions are 1.5 meter into 1 meter into 2 meter. So body dimensions are given and weight in water is also given. So weight of this body in water is given, that is 1962 Newton, and we are interested to find out weight of this body in air, also the specific gravity of this body. Okay, so as the dimensions is given, we can find out the volume of this body. volume of this body. So volume of this body will be simply into 1.5 into 1 into 2. So we can say that this is 3 meter cube. Okay, now as the weight of the body in water is given, means obviously the body is heavier than the water, because that's why we are feeling this much of extra force in the water. Because if the body is lighter than the water, then there is no weight of the body in the water is going to be feel in that case, because the buoyant force will be push the body in the upward direction. So here obviously the body is heavier than the water here. So this is given. Now as we know the volume and we know the body is heavier than the water, so obviously the body will be completely submerged in the water. So as the body is completely submerged in the water, this body will displace the water exactly equals to the volume of this body. Okay, this body will displace the volume of water exactly equals to the volume of this body. So we can also say that this is the volume of water displaced. Okay, so this is the volume of water displaced. So if we know the volume of water displaced, I think we can calculate what is the buoyant force by the water. So buoyant force, we can simply say that this is nothing, it's a simply weight of water displaced. So weight of water will be equals to specific weight of water into the volume. So we know the specific weight of water, this is 9810 into volume. Volume we also know this is 3. So this will be equals to, so this value is 29430 Newton. Okay, this is the buoyant force that is acting on this body. So as this force is acting in upward direction, and weight of the body in the water is given, that is 1962, that is acting in downward direction. So when the body will be in air, then there is no buoyant force, so obviously the weight of the body will be equals to the sum of weight of the body in the water plus the buoyant force. So by the use of this one, we can say that that is weight of the body in the air will be equals to weight of the body in the water plus the buoyant force. So this will be equals to 1962 plus 29430, and that will be equals to 31392 Newton. Okay, this is the weight of the body in the air. Okay, so we know the weight of the body in the air. Now we want to calculate the specific gravity of this body. So to calculate the specific gravity of this body, first we have to calculate the mass density of this body in air. So in this case, let's suppose, so first I'm saying the mass of this body. So mass of the body, we can say that is weight of the body in air divided by g. Okay, as we calculated here, so this will be equals to 31392 divided by 9.81, that is g actually. So the mass of the body will become 3200 kg here. So this is the mass of the body in the air. Okay, now we can calculate, I think, density of the body in the air. So this will be equals to what? This will be equals to the mass of the body divided by the volume of the body. Okay, so we know the mass, that is 3200, and we know also the volume, that is 3 meter cube. So this become 1066.67 kg per meter cube. This is the density of body in air. So as we know the density of this body, I think we can calculate the specific gravity of this body. So specific gravity of the body become the density of the body divided by density of the water. So this will be equals to 1066.67, and density of water at 4.4 degrees centigrade and 1 atmospheric is 1000. So we can say that the the specific gravity of the body will become 1.067. Okay, so obviously in this case you can also see here the specific gravity of the water is 1 and the specific gravity of this body is 1.067. So this body is denser than the water, so this will also going to be completely submerged in the water, and this is going to be sink down in water. Okay, so point is clear. Now we will understand the concept of stability of submerged and floating bodies. So before understanding the stability of submerged and floating bodies, we have to understand the concept of stability. So here I am providing three sections here, three types of equilibrium system. First I am saying stable system. Okay, and I'm dividing this one. This is not the straight line, but okay. Second is unstable. And third we are defining neutral system. So this is neutral system. Okay, now so how can we define a system is a stable system? So we can provide the definition like that. Let's suppose if we are saying after the initial disturbance, if we are disturbing some body, so after the initial disturbance, if the forces and moments on the body are working in such a way that the body come back to its initial position, then that equilibrium is defined as stable equilibrium system. Means we can take an example here. Let's suppose there is a concave surface here, and this concave surface, let's suppose I am considering a ball here. Okay, now if you are disturbing this ball from its position, in that case the forces and moments will work on this ball in such a way that is after some oscillations or after some time the body will gain its initial position. So actually this type of equilibrium is defined as stable equilibrium system. Okay, now so what is unstable system? For unstable we can provide a definition like, if the after disturbance the forces and moments are working on the body in such a way that is the body is going to be disturbed more and more and it's never regain its initial position, then it is defined as unstable equilibrium. So we can also take an example here. Let's suppose this is convex surface I'm saying. So this we are considering convex surface. Now let's suppose here is a ball in this case. So if you are disturbing this ball from its initial position, then the forces and moments are working on this ball in such a way that is this ball is going to be disturbed more and more, and obviously this ball will never gain its initial position. So this is defined as unstable equilibrium. Now third category we are defining is neutral equilibrium. So what is neutral equilibrium? So we can provide the definition that if after the initial disturbance there is no net forces and moments are working on the body and body is gaining some new position, then it is defined as neutral equilibrium. Means we can say that this is our flat surface and ball is here. Okay, so if you are disturbing this ball, there is no net force and moment is working on this ball. No net and force working on this ball that will try to bring back the ball to its initial position, or the forces that will try to disturb this ball more and more. So there is no net force and there is no net moment. So after some time, this body or this ball will gain some new position. So this type of equilibrium system is defining neutral equilibrium system. Okay, so we have three categories: stable, unstable, and neutral one. So first we will try to define the stability of submerged bodies. Okay, so first we are defining estimate for submerged bodies. So I'm saying this is for submerged bodies. Okay, we are taking all three cases here. So first of all, we are defining stability of a submerged body. How can we define the stability of a submerged body? So let's suppose we are considering a parachute here. Obviously the parachute is completely submerged in the air. Here is the weight. Okay, now this is our parachute. It's okay, that's good, no problem. Now, so obviously we can say that there is the total force of this parachute, that is the total weight of this parachute is acting actually at this portion. So we can say that this is the center of gravity of the total weight is acting here. So we can say that here the total weight is acting here, that is obviously acting in downward direction. And the maximum displacement of air, we can say that here. Okay, so as the maximum displacement of air is here, so we can say that the center of buoyancy is acting around here, because these ropes and this weight is not displacing too much air, but the maximum displacement is of air is occurring here. So we can say that this is our center of buoyancy, and that I'm denoting this one by B point. At the center of gravity I'm denoting by G point. So the buoyant, due to the displacement of air, the buoyant force will act in upward direction. This is our buoyant force. Now for submerged bodies, we can say that there is a line of action of buoyant force and the line of action of weight will always be same, and this will be vertical here. Okay, so let I'm drawing this line here. So I am drawing it like that. Let here is our center of buoyancy. This is the line of action, and here the center of gravity. So the weight is acting over here, and here the buoyant force is acting. Okay, so this is the case here. So obviously in this case the center of buoyancy is lying above the center of gravity. So let, due to some wind forces or wind gust, this is going to be disturbed here. So this point B will shift around here, and this line is going here, so point G is going to shift here. So this will look like this one. So point B is going to be, let I'm using different color here. So I'm saying point B is going to be here. So this is our B point here, and in this case let our point G is going to shift here. This is here. Okay, so in this case the buoyant force will act in upward action here, and in this case the weight is acting over here. So in this case, after the initial disturbance, you can see here this force has some distance of initial line of action. This buoyant force has some distance from initial line of action of this one. So this force FB into this distance will creating a counterclockwise moment here. You can see here this FB into this distance is creating a counterclockwise moment here, means it is generating a moment like that. Okay, now obviously this weight is also having some distance from its initial line of action, this one. So you can see here this weight into this distance is also creating counterclockwise moment here. This weight is acting downward here, so this distance, so about this point we can say that this is creating counterclockwise moment here. So this is creating this moment. So in this case you can see both buoyant force and weight are creating moment in such a way they are just trying to bring back this body its initial position. The moment is counterclockwise here, so they are trying to the body in initial position. Let if I'm saying this is B dash and G dash, so here B is trying to approach, sorry, B dash is trying to approach B and G dash is trying to approach G here. So when this point is going this side here like that, let's suppose this is B double dash, so the buoyant force will act here, and this is G double dash, so the weight will act here. Okay, now in this case you can see here this FB into this distance will create a clockwise moment, and this weight into this distance will also create a clockwise moment. So the buoyant force and weight are creating clockwise moment, and so in this case B double dash will try to approach B and G double dash will try to approach G. Means after the initial disturbance, the forces and moments are acting in such a way they are trying to bring back the body to its initial position. So obviously in that case we can say that is the body is in stable equilibrium system. And for the submerged body, a body is said to be in stable equilibrium system when the center of buoyancy will lies above the center of gravity. Okay, we can say that a submerged body is said to be stable body if the center of buoyancy will lies above the center of gravity. So this is the case of stability. Okay, let in our next case, in unstable case, that we are saying this is our line of action of buoyant force and the weight, but the condition is reverse. That if here I'm saying at this point this is the center of gravity, so the weight is acting over here, weight is acting over here, and this is the center of buoyancy, so we are saying this is the buoyant force acting here. Okay, so in this case the center of gravity is lying above the center of buoyancy. This is the reverse case of this one just. So let after providing the initial disturbance, so let I'm saying this point is going to shift here, that I'm saying this is G dash point, so this I'm saying this line of action is going to be tilted like that, and let this B point is going to be shift here, let this is B dash, so the weight will act here and the buoyant force will act here. Okay, so now in this case you can see this weight having the distance from the initial line of action, and this weight into this distance about this point is creating what? Creating a clockwise moment. So it is creating a clockwise moment. So due to this clockwise moment, this body is going to disturb more and more. Similarly, this buoyant force into this distance about this point is also creating a clockwise moment. Okay, so this line is also going to disturb more and more. So means in this case the weight and buoyant force are acting in such a way that is they are simply disturbing the body more and more. So in that case the body will never gain its initial position, because due to this forces moments G dash is going to be more far away from the G, and similarly the B dash is also going far away from the point B, so the body is going to disturb more and more. So in this case the body or submerged body is said to be in unstable equilibrium state. So we can conclude that is a body is said to be or a submerged body is said to be in unstable equilibrium if the center of gravity lies above the center of buoyancy. Okay, so if the center of gravity is lying above the center of buoyancy, then a submerged body will be in unstable equilibrium. Okay, so in our third case, so let in our third case I'm saying it is happening like that. Let this is the point that is I'm defining center of gravity. So obviously weight is acting over here, and the center of buoyancy is also this point. So both the points are coincide here. So the buoyant force will act here in upward direction. So there is no distance between the center of buoyancy and center of gravity. So if you disturb the body, I think there is nothing is going to be changed here, and both the points will be coincide here. Like in the previous cases, as we disturb the body, there are some distances here, but in this case there is no distance here. Means, so if you are disturbing the body, so as there is no gap between the point B and G, so obviously there is no distance, so there is no moment here. And also as there is no moment here, so if there is no moment here, so body is not going to be trying to back its initial position, or it's not going to be disturbed more and more. So obviously in this case there is no net force and there is no net moment, so the body will gain some new other position, but the condition remains same. We can say that after the disturbance, this point become the B dash, and the buoyant force will act here, and the similar point will become G dash, and weight will act here. So now as there is no net force and net moment, these point B dash and G dash are not trying to approach this one or not trying to further go away from this point. So this type of system is defined as neutral equilibrium system, or a submerged body is said to be in neutral equilibrium if the center of buoyancy and the center of gravity are coincide. Okay, from here we can conclude that is submerged body is said to be in neutral equilibrium if the center of buoyancy and center of gravity are coincide. Okay, so I think the point is clear about the submerged bodies. Next we'll understand about the floating bodies. Now to understand the concept of stability for the floating bodies, first we have to understand the concept of metacenter. Okay, so let's try to understand the concept of metacenter. Okay, so first here we try to calculate what is metacenter is. So I'm writing metacenter. Okay, now so let's suppose this is our free surface of fluid, and some body is floating in this fluid here. Okay, so this is the floating body, and let's suppose this is the axis of this body. Okay, and we are saying this portion here, this point is I'm saying X, this point is also I'm saying X here. Okay, and this center, I'm saying this is O here. Okay, so now I think we can easily calculate what is the center of this, the center of gravity of this body by this body configuration. So we can say that around here is the center of gravity. This is center of gravity here. Now the center of buoyancy is actually the center of gravity of displaced fluid. So in this case I think the displaced fluid is this part, that is from the x-axis line to this lower face. Okay, so for this submerged part, the center of gravity will be, sorry, center of buoyancy will be here. We are defining the center of buoyancy is nothing, it's a simply center of gravity of submerged fluid. So this is actually center of gravity of submerged fluid, and we are defining this is center of buoyancy here. Okay, so from the center of gravity, weight of the body is acting. Okay, and from the center of buoyancy, buoyant force is acting, that is acting in upward direction. So buoyant force is acting in upward direction and weight of the body is acting in downward direction. So from here we can say that this line is simply the line of action of buoyant force and weight of the body. Okay, buoyant force is acting along this line and weight is also acting along this line. So this is the line of action of buoyant force and weight of the body. Okay, so let disturb the body here. So as we are disturbing the body here, so this is our free surface here we are defining, and after the displacement the body will look like this one. So after the disturbance the body will look like this one. Okay, this was the axis, or actually we defined this was the initial line of action of buoyant force and the weight before the disturbance. Actually this is this axis, and I think as this body is going to be tilt, this x point be going out here and this x point is going to be in here, so it will look like this one. So this is our O point, this was our x point of left hand side, this is our x point of right hand side. So this x point is going up here and this x point is going down here. Okay, now obviously the center of gravity of this body is not going to change, it will remain same here. So here is the center of gravity, this is the center of gravity, and weight is acting over here. But now in this case you can see here, and before the displacement the displaced fluid was in rectangular form, but after the displacement new points that I'm saying this one and this one are the y points, and in this case the submerged part is like a trapezium. So for the rectangle this was the center of gravity, that's why we define this the center of buoyancy of fluid, but in this case the center of buoyancy will be for the trapezium part. So let's suppose if I'm saying around here this B is going to be shift. I know this is not looking good here, but for our calculation purpose this is okay here. So B is going to be shift here according to trapezium. Okay, so for this trapezium body this is our new B here, that I'm saying this is B dash, and buoyant force will act here. Okay, now so the value of buoyant force FB and this FB will also be same. Why? Because as this left side, as this X is moving out from the fluid, then this much of body is coming out from the fluid. But at this right side, as X is moving down in this fluid, so the same volume of the body is going inside the fluid. So the same volume is out of the fluid, same volume is going inside the fluid. So I think the weight of fluid displaced by this body after this disturbance will also be equals to the weight displaced of fluid by this body before the displacement, because volume in both cases is same. In this case this is the volume, and in this case the volume of body coming out from the fluid and volume of the body coming in of the fluid is same, so the buoyant force in both cases remain same. But here the line of action of this new buoyant force is going to change. This is the new line of action of this buoyant force. Okay, and this line was the initial line of action of this buoyant force before the displacement. So here we are defining a point that is termed as metacenter. Metacenter is a point where the line of action of buoyant force before the displacement or before the disturbance and the line of action of buoyant force after the disturbance are intersecting. So this point is our metacenter, and I am defining this point is point M here. So what is metacenter? Metacenter is simply, so that if I am saying this is the line of action of buoyant force before the displacement or before the disturbance, and this is the new line of action of buoyant force after the disturbance. So that I'm saying this was the B here, this is the B dash here. So this is the buoyant force that is acting over here. So this was the initial line of action, this one, this is the after the disturbance. So they are intersecting at this point, and this is defined as metacenter. Okay, and around here is our center of gravity, so the weight is acting over here. Now, so this point we are defining metacenter. So I'm repeating the definition of metacenter. What is metacenter? Metacenter is simply the intersection point of line of action of buoyant force before and after the disturbance. Now we will define the stability of floating bodies based on the metacenter and center of gravity of this body. Okay, now the gap between the metacenter and center of gravity of the body is defined as metacentric height. Actually, this gap is defined as metacentric height, or I'm simply writing metacentric height is what? This is equals to distance between G and M. Okay, this is defined as metacentric height. Okay, so first we try to define the stability of this floating body. So I'm taking our table here. So this we are defining for the floating body. Okay, this was stable, this was unstable, and this is neutral. Okay, so if we are saying a floating body is a stable body, then the condition will be this one. How? So let's suppose this is our metacenter, this is our center of gravity, so weight is acting over here, and from this side this is the buoyant force acting here, this is the center of buoyancy here. Okay, so this is our center of buoyancy, this is our center of gravity, and this is our metacenter. Okay, these are the points. Now look the condition here. When we are saying the metacenter is above the center of gravity in this case, so you can see here this buoyant force into this distance. So this buoyant force into this distance is creating a anti-clockwise moment here. So this force acting in this direction, this is the distance here, so they are creating anti-clockwise moment here. So the moment created by the buoyant force is anti-clockwise. So means this buoyant force will try to bring back this body in its initial position. So it is pushing this body in this direction back. Similarly, this weight into this distance also creating a moment about this point. So this weight into this distance is also creating a moment, and this is also in anti-clockwise direction because this weight is acting in downward direction. So this weight into this distance is creating anti-clockwise moment here. So this moment is also anti-clockwise moment. Okay, so both weight and buoyant force are creating anti-clockwise moment, and that's why they are trying to this body to bring back in its initial position. That's why we are saying that is, if the metacenter is lying above the center of gravity, in that case the floating body will be stable body. And there is one more term. If we are saying the metacenter is above the center of gravity, then this height, that is metacentric height, will say positive. So I'm saying here GM is positive. Okay, so in this case metacenter is above the center of gravity, metacenter is above the center of gravity, so in that case a floating body will be a stable body. So let's take the reverse case. That again I'm saying here. So here is our center of gravity, so weight is acting over here, and here is our metacenter. So the buoyant force, so this is the center of buoyancy here, so buoyant force will act here. Okay, so this is the line of action of weight, this is the line of action of center of sorry, that is buoyant force. So let again check the moment. So here now this buoyant force that is acting in upward direction and into this distance about this point, you can see here this buoyant force that is acting in upward direction and into this distance, it is creating a clockwise moment here. This buoyant force into this distance, buoyant force is acting in upward direction, so this buoyant force into this distance is creating a clockwise moment about this point. So actually buoyant force is trying to disturb this body more and more. Okay, now this W is acting in downward direction and into this distance, so this W into this distance, so this is also creating a clockwise moment about this point. This W is acting in downward direction and this distance into this distance, it is creating also a clockwise moment. So actually G is also creating a moment such that it will also try to disturb this body more and more. So both the forces are creating in such a way that is they are trying to disturb the body more and more. So in that case a floating body is said to be in unstable equilibrium. And obviously, as we are saying, a floating body is said to be in unstable equilibrium if the center of gravity is lying above the metacenter. And as the center of gravity is above the metacenter, here we will define that is metacentric height will be negative. Okay, now our third case. So let's suppose again I am considering the same case here. And in this case that I am saying this is our G, so the weight is acting over here, and the similar point is also M, metacenter, this point. So this is our buoyant force acting at the center of buoyancy that is acting in upward direction. Okay, so in this case the center of gravity and metacenter are coincide. So as both the points are coincide, there is no gap between the weight and the buoyant force, as there is a difference here between the buoyant force and the weight here, so they are creating moment here. In this case also weight and buoyant force some distances, that's why they are having some moment here. But in this case there is no distance between the weight and the buoyant force, so the moment produced by these forces will be zero. Means these two forces are neither creating a clockwise moment or creating a anti-clockwise moment, so they are producing no effect here. So if the body is a neutral body, in that case the resultant force or net forces and the net moment will be zero, so the body will remain same in this new position after the disturbance. So means we can conclude that that is a body is said to be in neutral equilibrium, or a floating body is said to be in neutral equilibrium if the center of gravity and metacenter are coincide. Okay, so if both the points are coincide, we can simply say that that is the metacentric height will be zero in this case. Okay, so I think all the points are clear. And please guys, like the lectures, subscribe the channel, comment your doubts, and please share the knowledge as much as you can. Thanks for watching. Take care of yourself. See you in the next lecture. In the next lecture, we will start the kinematics of fluid. Till then, take care of yourself. Thanks again.